Hello, everyone. So today is my last lecture, and I think just like me, you might be also very tired. So I I will try to do something nice and pedagogical, but I confess that at some moment I will just flash some results, and because I would like to finish this presentation by presenting a very nice application of this framework, which is very different from what we saw so far, right? Because we're basically looking at this theory as a classical theory. If we think that we have probability vectors, stochastic matrices, and so on, and then we could ask what is quantum in this approach. So my goal is to actually end up like with an example, but before this, I will also show some applications. And when I show these applications, I think it will be a bit not so nice, because I will just open up some pictures there and then say a few things, and then I hope you can believe that those things that I'm saying is true. If not, later on we can discuss, and then I can go through it in more details with you. So let me start with a very rough summary about what we discussed today. Yesterday. You see that I'm still sleeping. So basically, yesterday we saw that solution, a particular solution of the problem that I posed in the first class, whether there exists a thermal operation between two different states. And to get this partial solution, what we assumed was that we were dealing with energy incoherent states, those that commute with the Hamiltonian, so they are diagonal in the energy eigenbasis. And then they can be described by a probability distribution, a vector of probability that I called populations. And then we also assume that beta was equal to 0, meaning that we are looking at the infinite temperature limit. And we focus on this because basically we derive a collections of theorems, and my goal today is to look at those theorems and have a bit of hope to generalize them for finite beta. So basically, the first thing that we saw was that when we are looking at beta equals 0, basically the thermal distribution becomes the uniform distribution that I'm denoting by eta. So this is just a maximally mixed state. If the system has dimension d, this would be 1 over d, 1 over d. And then since the process that I'm considering constrain the fact that if we act on it in a thermal state, we have to get back a thermal state. But now if this thermal state is this uniform distribution, we come to the conclusion that this matrix here has to be bistochastic, right? Bistochastic here meaning that if we sum over the columns, this goes to 1. If we sum over the rows, this also goes to 1. And then at that moment, I invoke many theorems that it was developed around the 40s, 50s. The first theorem actually solves our question. So basically assume that we have three states, rho and sigma. These three states are energy incoherent, so they can be equally described by probability vectors P and Q. And there exists a bistochastic matrix mapping P into Q if and only if P majorizes Q. And we saw that majorization condition, it's pretty simple. We just need to check d-1 inequalities, and we have a very nice, easy way of checking those inequalities. And another interesting result that we saw is that, well, bistochastic matrices, they are somewhat special because we can break down into a finite product of T-transforms. Why this is nice? Because those T-transforms are convex combinations between identity, doing nothing, or swaps. So basically here, the idea was that I have this stochastic matrix here, which in principle would act in many levels of my system. But then what this theorem says to us is that now I can decompose this into a finite sequence of operations that act non-trivially onto two energy levels on time, and then identity everywhere. So this kind of gives us a way, if you think about the sequence that we need to perform some, well, thermalization. Although here it's still beta equals 0, right? And then another important theorem that I discuss is the Birkhoff-Polytope, which says that bistochastic matrix forms a convex set whose extreme points are permutation matrices. And basically what this theorem is telling us is that if you take your favorite bistochastic matrix, you can always write it as a convex combination between permutation matrices. And permutation matrices by this guy here can be decomposed into a product of T transforms. Well, after this then, we can collect these results and answer the second question that I posed in the first lecture, which is, suppose that you have a given bath, your state is prepared in this initial state P. What is the set of states that you can achieve under this allowed set of operations? Here, under bistochastic matrix. Because now we can just combine Hard-Littlewood Polya theorem with Birkhoff and get to the conclusion that now this so-called future thermal cone is simply the convex suite of permutations of my probability distribution. For example, if I start with a state whose population is 0.7, 0.2, 0.1, then we are sitting precisely here. So permutations of these states will be extreme points of the future thermal cone, and everywhere that I can go via bistochastic matrix is represented in this green area here. And this is what I'm calling future thermal cone. So in other words, all states lying here are majorized by my initial state, which is precisely what we see here, right? It's the same state. Something that I didn't mention, but it's equally nice, is if you look at the reverse question, what is the set of states that can achieve your initial state? Those are called past cones of P, and they are depicted in blue there. And then states that you can't transform your initial distribution nor can be transformed to yours, it's in that red region, and it's called incomparable region. And the fact that we have an incomparable region is a finite size effect. And one of the manifestations that now that we are far from this thermodynamic equilibrium, there's not a single law, but a family, D-1. So do you have any question concerning this first part? Yeah? So this is a very nice question. So basically, so what we know, for example, yesterday, so it might be that you need just one T transform, but it might be that you need two T transform, but there will be extreme points that you need, let's say, D-1. So for instance, if I, yes, let me. So if I'm here, for example, to go to this other extreme point here, I just need to apply pi on 1, 3, 1, 2. Wait. How I'm labeling? So this is 0. So yes, 2, 3 on P. Okay, but then if I go here, then, well, you can think that, well, first you come here and then you apply now another T transform, which is just a permutation, right? And here I think it's 1, 2 or 1, 3. Yeah, it's 1, 2, I think. But then for larger dimensions, there will be extreme points that you have to have access to more products of T transforms. Good. Okay, so now then let's look at the case that beta is different from 0. So finite beta. Basically, okay, so So in this first class, I started already with this theorem by Horodetsky, which says that there exists a Gibbs preserving matrix mapping P into Q. Well, wait, yes. Okay, this I didn't mention, I think. P, yeah. Yeah. So yeah, sorry, I didn't mention this theorem in the first class, but here, this will be our starting point from this class now. So basically, this theorem kind of solves the question that we pose, whether there exists a Gibbs preserving matrix mapping P into Q. And the condition here is, again, a variant of majorization. This variant is called thermomajorization. I will define in a bit. And what this result tells us is that, well, we can construct a Gibbs preserving matrix mapping P into Q if P thermomajorizes Q. And then I'm at the language of stochastic matrices preserving the Gibbs state, but we could go one level up and construct a thermal operation, right? Because we have this theorem that I mentioned in the first class, which has this equivalence between thermal operations and Gibbs preserving stochastic matrices. So now the question is, okay, what is this thermal majorization condition and how hard it is to check whether you can transform P into Q, right? Before I define this, again, we will have to check D minus 1 inequalities. We have a very powerful method to do this. If you remember from the class yesterday, we had these Lorentz curves, majorization curves. Here you have an equivalent, a thermal majorization curve, and this will give us the answer of this question. And this is very, very actually interesting, right? Because basically we are far from equilibrium, we have minimal assumptions, and still we can give a very simple answer for this problem. Well, yesterday I defined majorization as we said that given P and Q, we say that P majorizes Q if the following inequality holds. So let me write it here. So basically, we say that P majorizes Q if only if the cumulative distribution of P ordered in non-increasing order is greater or equal to the cumulative distribution of Q ordered in non-increasing order. And basically, we check for each K going from 1 to D minus 1. I put D here because the last case is trivial, because since those are probability distributions, this will sum to 1. And now I will make an easy generalization of this by considering a majorization relative to the thermal distribution. What does that mean? It means that here we could think that we have a majorization relative to the oops. Yes. Technical issues. Yes. Yes, okay, so let me go a bit far from the blackboard. So we could interpret this as a majorization relative to the uniform distribution. What do I mean? Imagine that we have our uniform distribution, which is 1 over D everywhere. Then we take P, and then we divide it by eta, entry-wise. So P1 over eta 1, PD over eta D. And then we order this vector in non-increasing order. But then, again, this is just like a renormalization, right? Because all eta 1s or all etas are precisely the same. It's 1 over D, so I'm just renormalizing stuff. So it is precisely this K that appears in the x-axis of the majorization curve that I showed yesterday. Well, for thermal majorization, instead of dividing by eta here, we will put the thermal distribution. And then we ordered in non-increasing order. So let's suppose that we have P we have Q, and we have our thermal distribution gamma. So first, we consider this beta rescaled version where we take P, take the ratio with gamma, so we have P1, gamma 1, P, D, gamma D. Now things will be different, right? Because a gamma I will be E2 minus beta EI divided by its partition function. And then I order this guy in non-increasing order. And this vector ordered in non-increasing order will be, I will give a special name for it. I will say that it's the beta version of P. Okay? So there's an easy way of writing this vector here because we can define this notion of beta ordering, which is precisely a permutation pi, which when acts on P, orders it on non-increasing order, right? After renormalizing. So basically this could be something like to be P, pi minus 1, okay, I'll take this, pi minus 1 over 1, pi minus 1 over D. So what this is telling us is that, okay, I find this beta ordering, and then I write my initial distribution according to this ordering. So let me give an example. Suppose that I take this ratio, and then suppose that you consider a 3-level system, and I take this ratio, and then I see that the ordering is 2, 1, 3, meaning that the second entry is larger or equal to the first entry, which is larger or equal to the third entry. So then I take this permutation and then I order my initial vector according to it. It's very, very simple. And now we are done, because if we want to know if P thermomajorizes Q, we just need to build the thermomajorization curves associated to those two states. Again, the thermomajorization curve will be a piecewise linear function, and whose points are simply take 0, 0, and then with. So in the x-coordinate, what I'm going to do is take my thermal distribution also ordered in beta order, together with my initial vector also ordered with respect to the beta ordering there. Just this. So those are the points of this curve. Okay, this is mathematically incorrect. Yeah. Just this. So let me just give you an example. Suppose that my ordering is 1, 2, 3. So suppose that my beta ordering is 1, 2, 3. So this means that here in the x-axis, I have gamma 1. In the second point, I have gamma 1 plus gamma 2, right? This is what is saying here. And then in the y-axis, I have my P1. So I will join these 2 points. I have an elbow here. Then here, I will have P1 plus P2, and so on and so forth. If the dimension of the system is 3, this goes to 1. Yeah. And this is precisely like a majorization curve. If we think that in the x-axis we are putting uniform cumulative versions of the uniform distributions, right? Well, but it could be also that the vector that I'm looking at, let's say my vector Q, has beta ordering 2, 1, 3, for example. Well, if this vector has this ordering 2, 1, 3, what we do is that, well, first, gamma 2 will be here. Then my P2, let's say my Q2 would be here. So say that this guy is here. Then the next is gamma 2 plus gamma 1, which is precisely this guy here. This would go here, and then 1. And here we see a different feature that we didn't see in the majorization curves, right? Because there, all then had the same ordering. Here, basically, we allow for different beta orderings. But then, okay, we have many different types of beta orderings, and then if now the beta ordering was 3, 2, 1, then gamma 3 would come here, and then I would proceed in the following in the same way. So then the idea is that P thermomajorizes Q if and only if its thermomajorization curve is always above the thermomajorization curve of Q. And this is some sort like of second law of thermodynamics, right? Because basically I'm telling that if I would like to transform some state P into Q under the action of a thermal operation, we have to build those curves and then compare those things. And this is the necessary and sufficient condition to answer this question. Good. So this, at first glance, it might look hard, but it's pretty simple. In the notes, there's some examples where I show this. Some questions, or is it okay? Perfect. Good. So, yes?
Classical majorization basically know that this is the unique way of defining this.
Yes. What do you mean by defining?
Kind of like defining this thermomajorization is the only way of doing it.
Yes, exactly. Yes. So here you define majorization relative to the thermal distribution. And once you get that this distribution is your fixed point, you fix the majorization. This is very good question, yeah. This is the only way, yes, exactly, yes. Yes, sure. So basically, thermal majorization consists of just building those curves, right? And the procedure to do this is, so let me. Yes. So let's say that we have some initial state, which is 7, 2, 1. So yes. Some initial state like this. Let's say that we have a thermal state, which is 3, 2, 1. This, right? So basically, the method is like, first, you ordered P with respect to gamma. And what do you do is that you take P and divide it by gamma, and then ordered in non-increasing order. So this is entry-wise. So first, you have 7 over 3. 2 over 2 is 1. 1 over 1 is 1, right? And then here you have some, I'll just put some proportional coefficient. So here, basically, we know that 7 over 3 is larger than 1, and this 1 is equal to 1 here, right? So the beta ordering of this state is precisely 1, 2, 3. Simply because the first element is greater or equal to the second element, which is greater or equal to. So then what you do is that, so I do this. So what I do now is that I take my state and write with respect to this ordering. In this case, it's trivial because it's precisely the same ordering that this initial state is already written, right? But let's suppose that this guy was here. Yes. So then the ordering would be 3, would be 3, 1, 2, right? So this vector ordered in beta ordering, this would jump to the first element here. No, yes, when I Sorry, it was a mistake. It was I should put labels. We use the beta ordering. Yes, yes. Mm-hmm. Well, no, right? Because basically, different vectors, they can have different orderings. So for example, if I take this vector here, 7, 2, 1, and if I take 4, 6, and 0, I'll put some normalization here. And then I take the same thermostat, 3, 2, 1, some other normalization. We see that when we take the ratio between your state and the thermal distribution, that you have different orderings. Yeah, I know that at first glance this might be confusing, but we have a very easy way of plotting those things. It's just following some predefined rules. Okay, nice. So basically, what the claim that I'm making here is that we are answering precisely the question. Let me clear out this mess. We are precisely answering the question whether there exists a Gibbs preserving matrix such that if I take P, I get Q. And the answer here is precisely that P has to thermomajorizes Q. Good. And now so basically we know what is the necessary and sufficient conditions for state transformation under Gibbs preserving matrix. The natural question is if we can now generalize those other theorems. Because if we can, it would be really nice, right? Because basically, at the language of maps, if we could generalize Moorhead-Littlewood-Polya theorem, we would be able to get this thermal operation and break into smaller pieces of small unitaries which act non-trivially in only 2 energy levels, right? But, well, unfortunately, shall I put like a theorem? So there's a theorem which shows that there exists thermal, well, let me put it. So there exists process in which you can map P into Q via thermal operations that cannot be broken into elementary thermal operations, where elementary thermal operations are precisely these thermodynamic generalizations of T transforms. And so basically what we are learning here is that basically, as I will explain in a second, is that if we have access to the future thermal cone of my initial state, there will be extreme points that I cannot achieve just by transposing different energy levels, different elements of my initial distribution. Okay, so let's discuss a very simple and illustrative case, or just let me flash as I said, and then it is carefully discussed in the lecture notes. So suppose that we have a bit with population P, 1 minus P, we have a thermal bath at inverse temperature beta, and then we try to ask what is the set of states that we can achieve if we start with this initial distribution, and we are performing thermal operations. Well, in order to check this, we need to look at the thermomajorization curves, right? So basically, what you do is that, well, you write the thermomajorization curve of your associated state P here. To do so, say that we have some thermal distribution with values gamma 1, gamma 2. So first, we write this vector in beta ordering. So here, I will just put So let's assume a beta ordering. Let's assume that the beta ordering of my state is the easiest one, is 1, 2. So this means that here I have gamma 1. So here I have gamma. So yes, since it's just a qubit, I write gamma 1 minus gamma 1 minus gamma. This is gamma, this is p. Then I get this. This is 1. This is 1. And this is 1. Okay, very simple. Yes, so now to construct the set of achievable states, I have to look to the following condition. We could assume that we have some Q, and then we can try to put Q inside to try to fit the thermal majorization curve of Q below this one, because I want this state to be in the future of P, but then I have to do this in an optimal way, right? What does it mean in an optimal way? It means that I have to fit this guy here in a way that this guy is almost in the verge of not being thermal majorized by P. This is a very sloppy way of doing this. In the lecture notes, I discuss better how you can reasoning better on what I'm saying. But let's analyze our possibilities. And the possibilities are basically two, right? So so the first case is precisely when this Q has the same beta ordering as P. The beta ordering is 1, 2. So basically, the best that you can do is like if they have the same beta ordering, is to basically send to do nothing, right? If you have your state, because basically, in principle, you could construct a Q which is here, but you could also construct a Q which is a bit above this one or above. So for this beta ordering, basically, it's a bit trivial, the scenario. It's better to do nothing. Well, the interesting and non-trivial case is precisely when this Q has beta ordering 2, 1. Why? Because now we will have some gamma 2 here, and now I can ask what is the maximum value of, let's say, Q, such that its thermal majorization curve will fit below the thermal majorization curve associated to P. Well, and if we do the calculations, so it has to be something like this. If we do the calculations, we can find an expression for Q. This is very simple. It's just a basic geometry here. We find that this Q, which will be an extreme point of the future of this P, is simply given by 1 minus gamma for gamma P and 1 minus gamma P. And if I open up this gamma, so if I assume that this bit is described by Hamiltonian whose spectrum is 0 and 1, then this extreme point that, I'm sorry for this, I'll change the notation by p pi, is given by 1 minus e to minus beta, yes, beta p, e to minus beta p, like this. So what does that mean is that, well, I have a two-level system. The simplex is just a line. If I start at this state P, the best thing that I can do is to map this to p pi. And everything which is between these two states, I can achieve. Good. And this is the future thermal cone for this bit. Well, let's think for a bit. If we already know the solution for beta equals 0, right? We know that for beta equals 0, the best thing that you can do is a permutation. Well, if beta is equal to 0, this goes to 1, and then this is 1 minus p and p. So it is like a swap. And then we can make a simple exercise where we try to construct the Gibbs preserving matrix that sends p into p pi. if we do this, we get the beta swap, which is 1 minus. Okay. Let me highlight this matrix here, maybe above here. Which is simply like this. Yeah, just let me, okay. So yes, which is precisely like this, right? Which is, yes, swap. So this is called beta swap. And it's just a thermodynamic generalization of the swap. That's nice. And then we could ask again this question that I pose here, that I said that it's not possible, whether we could, in principle, decompose those Gibbs-Preserving matrix as products of beta swaps. And as I said, unfortunately, the answer is no. But then you can write another resource theories based on this type of operation, which is called elementary thermal operations, where you allow those beta swaps, and then you could repeat precisely the same ideas that I'm explaining, try to get the future thermal cone and so on and so forth. But the main thing here is that, well, only with beta swaps, we are not able to map all the extreme points of the future thermal cone of P. Okay, good. I was gonna give an example now, but I think I will first give the answer of the future thermal cone, and then I will come back to this. So let me think. So how is it going so far? Good? Perfect. So, Yes, I will give the answer now. Yes, yeah. So, but just let me, because I know that those things might sound complicated, just let me summarize very quick. So basically, we learned that the answer for transforming probability distributions with Gibbs-preserving operations is contained in thermal majorization relations. Then we asked if we could decompose this Gibbs-preserving matrix as a finite product of those beta swaps or convex combinations between performing a beta swap and identity, and I said that this is not possible. And then the question is like, okay, can I construct the future thermal cone of my state? And the answer is yes. And the answer is yes. And the way that you do this, I will just give you a gist, and then maybe I can flash how you construct this, the extreme points of your future thermal cone, and then I will give some examples. So basically, if we think about the qubit case that we are just working on now, so we had that this was gamma 1, we had that this was 1, P1, then this was 1, P1, yeah, P1 beta, gamma 1 beta. And then the way that we construct this, the extreme point for our bit was precisely analyzing the case in which I try to fit the thermal majorization curve of this state below my state in such a way that I'm doing this somewhat like optimally, right? Optimally, meaning that for that beta ordering, that would be the best state. Well, if my system now, it's not a two-level system, but it's a three-level system or a d-dimensional system, we can play the same game. But now we will have d factorial beta orderings, right? So what we do is that for each beta ordering, So let's suppose that my initial state, I will take a trivial case that has beta ordering 1, 2, 3 up to D. So the thermal majorization curve will be something like this. And now for each permutation in SD, which defines a beta ordering, I try to fit the thermal majorization curve of this associated state here in an optimal way, just like in the case of the beat. And when we do this, we will have those extreme points, like those p pi for each pi over here, right? And then this is just like doing some basic geometry to construct these p pi's. In the lecture notes, I tell you how you can construct those p pi's. It's simply just a very simple procedure. And I prove why this has to be the extreme points of your future thermal cone. A basic fact that I didn't say is that the future thermal cone is convex, so compact, so this is why you have extreme points, and this is why you can characterize those extreme points. Great. So what I'm trying to say here is that basically we fully answered the question that we wanted to solve, which is, well, if we have a system described by some density operator rho, some Hamiltonian age, and we are allowed to perform some thermal operation, that thing, the future thermal cone, with that description, give us the set of states that we can achieve under thermal operation. Nice. Then answering the question of Rafa, the idea is like how this set looks like and how this set behaves with the temperature. And this is what I'm gonna show it now. So here basically what I'm doing, I'm taking a state whose population, it's a 3-level system. The population is 0.7, 0.3, 0.7, 0.2, 0.1. So the state lies here. And we are interested in the green region. The green region is the set of states that we can achieve. And basically, I denoted this simplex in the following way. Here's my grounded state. So if we think in the majorization cones, here would be 1, 0, 0. Here is the second energy level, and there is the third energy level. So what I'm gonna do now is to go from infinite temperature to finite temperature. And without doing calculations, what do we expect to happen? Well, first of all, my thermal state is given by this, right? So let's assume that we have a 3-level system whose energy gap is 1 and 2 here. So basically my thermal state will be E2 minus to be 1, E2 minus beta, E2 minus 2 beta, 1 over Z, right? So it is like one parameter family which depends on this beta. And then basically, since thermal states, the first entry is always larger than the second entry, which is always larger than the third entry. So basically, thermal states lives in this chamber here. This is the uniform distribution. And basically, if I start changing beta, what do I expect is that this thermal state will go towards the grounded state. Why? Because I'm cooling the system. And the way that this thermal state goes towards the grounded state follows this curve over here. And then if we remember about the first class, well, thermal states are always containing the future thermal cone of your state. So this means that this green region will try to follow this path. But the interesting aspect here is that now I will break the symmetry. Why? Because those extreme points now, they will not be weighted in equal ways anymore, precisely because I have some betas. So what happens is precisely the following. So I start decreasing and then I see this behavior. So I'm fixing the initial state. Thermal state is evolving towards the grounded state because I'm cooling my system. And then what is going on is that the volume of this future thermal cone, which is a monotone, by the way, starts to decrease. Do you know why it decreases? Do you have some guess? That's a very good answer. But can you give me another one? I like the first one better. It's basically because we know that fixed points of this map is thermostates, right? And what is going on is that my thermostate is going very close to my initial state. So if I'm very close to my initial state, of course that the volume will be much smaller than if this is far, right? So basically what happens is that, okay, so this volume starts to decrease, to decrease, to decrease, up to the point that it goes almost close to zero. And then a phase transition happens and it starts increasing again. Until the moment that this guy is going towards the grounded state, and then those things starts to expand again. Of course that if I start with a different state, so let's say that I start with a state 0.1, 0. Okay, so let's do random, real, 1, 2, 3, and then I normalize this by the total, and then I will call this P, and now P is precisely this state. Let me increase this, way too big, P. So here goes my P, those are the energy levels of my system, and this is the temperature. If I put, let me put thermal cones. Do I see something here? Yes. So now I'm, yeah. The entropy in this case. Oh yes, you have a very nice behavior of the entropy because the entropy starts to increase, right? Mm-hmm. In which sense? Because you are applying thermal pressure. Imagine like this. So, well, in this previous case, imagine that you are starting very close to the maximum mixed state, right? And then you are going towards the grounded state. And so I will come back to this. Just let me plot the future thermal cone for this other state here. Just to, yeah. So basically, okay, let me now vary this temperature beta table. Now beta goes from 0 to 2. And then list animate. How does this look like? Okay, of course it will not work. Wait, it's a very strange thing. Yeah, I mean, so in this case, for example, which is a bit not so nice, since we started here, thermal states will go towards the grounded state. Our state, it's far from this from the thermal state, so its future thermal cone will always grow in comparison to the other state. Okay, that's nice. And so basically here I'm just flashing those results. But now that you know the extreme points, you could think about applications. Because basically here you really have a roadmap on what you can do with your initial state, right? If you are described by this probability distribution and you want to engineer some optimal thermalization or some optimal process, you can look at thermal cones. And this is more or less what I'm gonna try to convince you in a bit with other applications. Do you have any questions or, yeah? Oh, the critical temperature, well, I don't know from head you can solve it, right? It's precisely when your initial state changes its beta ordering. And here I'm saying, I'm calling this by phase transition, and my notion of phase transition here is this idea that my system change beta ordering. So this doesn't mean that this implies some changing some other physical quantity. Okay, so as I said, so basically here I'm giving the example for a 3-level system, but those results are valid for arbitrary dimensions. We can construct extreme points for arbitrary dimensions, and then we can play around with arbitrary dimensions. Okay, good. And since we have this framework, we could think about several different ways that we can use them. I will exemplify with a very simple one, mention another nice one that Raf and I used for this other work, and show other information theoretic applications that you can use this notion of thermal cones. Wait. Yes. So basically, with this framework that I present, we can also come back to another question in thermodynamics, which is this idea of work and heat, right? And we know that for quantum thermodynamics, it's not always easy to define work. And basically, the resource theoretic approach has its own definition for work, which is somewhat nice and a bit more clear, because it kind of doesn't depend on changing Hamiltonians, doesn't depend on the specific process. And the way that you can do it is precisely thinking as a state transformation. So assume that you have your initial out of equilibrium state, and then you couple a battery system. And this battery system can be thought as a qubit, but could also thought as a continuous variable system where you have different energy ladders and so on and so forth. And now what you ask is that what is the optimal transformation such that you thermalize your initial system and you charge this battery to some state W. So this you ask optimal W. So for example, we could imagine that this battery is a qubit system whose energy difference is basically W. And then we can ask how much we can fit the thermal majorization curve of this state into the thermal majorization curve of this state, right? And how much you can fit is connected with this W here. It's an exercise that I added in the lecture notes. And there, the first question is whether this transformation is possible. And as you see, this transformation will not be possible. You get that this W is equal to 0. Why is that so? Because if we think about the framework that we are discussing, we are looking at a single shot transformation, right? And basically, if we were able to map this state, to map this composite state into this one, it would be like if we are extracting deterministic work from some mixed state P. But then if you take this P to be a pure state, like this or like this, you can get some results. Or what you can do, which is very nice, when you assume that this guy is a mixed state, you have a battery system, and then you ask what is the optimal work, such that you send the first the first state to a thermal state, and this battery system is epsilon away from your initial state. So let me put it like this. So what does it mean? It means that this is for your battery. And you can try to see what is the optimal epsilon for extracting the amount of work that is contained in this out of equilibrium state P. Nice. And with this, you could also generalize for other standard thermodynamic transformations, such as what is the optimal work for cooling your system. If you look at this Landauer's principle, you could reformulate also the problem in this following way. And you could also use the same framework here to exercise Maxwell's demon, which is something that Raf and I did in this tutorial that we wrote some months ago. And then the idea there is now, the idea there is very nice, because basically in this tutorial we kind of present 3 different ways of exercising Maxwell's demon, and we treat using resource theories. And there is nice because you go beyond of making any assumption about your system. You just work at the level of density operators evolving under energy preserving. It is very, very nice. And then you can see what is the price that you pay to do so. It's also in the tutorial there. Well, so how much time do I still have? Half an hour, nice. So basically, we also apply the same framework for many different other tasks, such as, now it's the moment that I start flashing results. Let me, wait, where are these? Yes. So for example, you could think about the following problem. Imagine that you have two identical qubits. These two identical qubits are described by the same Hamiltonian. So this means that you have some degenerated energy subspace. And because this unitary is energy preserving, I can act on this degenerated energy subspace, right? And then the task that we posed there was like, can we generate entanglement from separable states using thermal operations? This is a bit non-trivial, right? Because basically we always see the environment as an enemy for us. And basically the point is that, well, the environment doesn't need to be necessarily an enemy. And in this paper, we kind of show how you can generate entanglement, the maximum amount of entanglement that you can generate it, and how you can do this. So just let me flash these two plots here. So basically, in the first plot, what we are showing is like, well, imagine that you have these two qubits, and first of all, you can ask what is the set of states that lie in this probability simplex that cannot get entangled under thermal operations, right? And then you quantify the volume of this set. And then you see, and then what we did was to characterize this analytically, give the necessary and sufficient conditions to generate entanglement with thermal operations. And then what you can do is to see what happens now if this environment, which starts in the infinite temperature, which is the worst case scenario, behaves when you start to decrease the temperature. And as you can expect, as this environment starts to decrease, smaller gets the volume of the set that cannot generate entanglement under thermal operation. Something that I didn't talk about is that we can also look at Markovian thermal process, meaning that now we assume that the evolution of my system is open. I assume that this BEF is very large, correlations quick decay, and I have a Markovian thermal process. And I can reformulate the same, more or less the same set of rules that we have here. But now, the necessary and sufficient conditions to transform a given initial distribution into some output distribution via some Markovian thermal process is given by this continuous version of thermal majorization. It's called, it is called continuous thermal majorization. But the nice point there is that there is a finite set of inequalities that you can check to say whether there exists a Markovian thermal process between these two states. And for Markovian thermal process, what is most interesting is that there are a universal set of elementary thermalizations that you can construct. And if you take your favorite open dynamics model, what we can do is precisely give you what is the set of universal gates that you have to use to construct the dynamics of the system without solving equations of motion. And then here we basically ask the same question: can we generate entanglement via Markovian thermal process? And then here we are basically looking at the volume of the set that you can generate entanglement and how this volume behaves as a function of the inverse temperature. Well, there are other applications which is very nice, which is this following one. So basically on this first picture here, we have a thermodynamic process that we don't impose any constraint. It's basically thermal operations. So it might be that your evolution is Markovian or non-Markovian. Everything that you can do lies here, right? It is precisely what I discussed this class. But now if you look at Markovian thermal process and look at its future thermal cone that we can also build, you'll see that now these things shrink much more. And the difference between these two regions arise from memory. So basically in this region here are non-Markovian process. And then the question was like, can you write down a thermodynamic framework which allows you to do thermodynamics in this regime? So let's assume that you have some memory. You use some quantifier for this memory. What can I learn thermodynamically speaking from it? And then we provide a framework for this. And we also showed how you could map a Markovian dynamics to a non-Markovian one by having access to your heat bath. So basically, we had this very nice result where we assumed that we had this initial state here, and then we had the bath. And then the question that we posed was like, what happens if we have some control under the degree of freedoms of the bath? And then in such a way that I take the system, I couple with the bath, and then I use these partial thermalizations here. I use a Markovian thermal process. But then I don't discard those particles of the bath. I allow myself to have a bit more of control, such that if I do this over and over until the moment that I have all the degrees of freedom of the bath, I can map this Markovian to non-Markovian one. Yes, good. Okay, so now to finish, I must say that I bombard you and I flash many different things. It might be hard, and I will be here, we can discuss those things. But before I finish this presentation, I just wanted to show something very nice that we can also learn from this framework. But before I continue, is it okay if I? Yes. So good. I still have how many minutes? That's perfect. Yes. Yes, this is a very good point. So far, I just look at incoherent state, classical states, and basically my approach was like, I can generate some quantumness from classical states and energy preserving unitaries, such as entanglement, such as magic, but then indeed, I'm fated to only work with the classical thing. For a qubit, with coherence, I can still construct the future thermal cone, the past, and the incomparable, and they are in the lecture notes. But then now it's the time to ask, okay, can we learn something new? Can we learn something quantum from this framework that I'm introducing to you? And then here, I would like to come back to the first question that I started when I defined quantum thermodynamics in my first class, which is like, how do quantum features such as entanglement or coherence affect thermodynamic process, if they do? We know from the literature that actually they do. There are many papers which shows that entanglement can give you a boost for quantum heat engine, and entanglement will have signatures for phase transition and so on and so forth. But then those are very tailored for specific models. So the idea again is the following. You give me some unknown state and some arbitrary thermodynamic process. Can I probe the presence of quantum correlations just by looking at the quantities which are accessible for you? And to motivate this question, I would like to start with a case that all of you already know quite well, which is precisely Clausius' formulation for the second law of thermodynamics. So basically, Clausius' formulation says that if we have two thermostates at two different temperatures, macroscopic systems, one characterized by some temperature T1, the other by some temperature T2. If we put them into contact, then because of this temperature difference, heat will flow from the hot body to the cold one, right? Well, but now we could try to make this a little bit more interesting and assume the following scenario. Suppose that we have just, doesn't need to be 2 qubits. I will just make with 2 qubits to exemplify. Suppose that now I have 2 thermal qubits. So let's say that I have 1 qubit at some thermal state at temperature T1 and another qubit at some thermal state at temperature T2. Well, if then I put them into contact, turn on some interaction, we know that from Clausius formulation that heat will flow from the hot body to the cold one. But what happens if now this state is prepared in a correlated state, but locally they are thermal? So what it means that basically if I look at the whole state is correlated, but then if I look at them individually, meaning that I trace, let's say, subsystem 1, they are thermal. So this means that this would be like traceless, this psi here, okay? So they are locally thermal, but globally correlated. So this is a question that it was asked many years ago, and it was answered by Dave Jennings and Terry Rudolph. And what we learned that in this case, basically we can reverse this heat flow by paying the price by having correlations. Meaning that now heat can flow from the cold body to the hot one at the price of correlations. And it's very interesting because basically we can generalize Clausius formulation to account for those correlations. And the most interesting aspect about all this is that there was this very beautiful experiment which was done at CBPF, demonstrating this anomalous heat flow. So this is an example of how quantum features can affect thermodynamic process. But then we could ask another question, which is like, okay, but are those features really quantum? If I allow myself to have some, if I allow myself to bring another system which will not interfere on the dynamics of system 1 and system 2, but it will be like an intermediator of this transformation, could I somewhat say what is the nature of this correlation? And by doing so, people realize that actually classical correlations could also reverse this heat flow. So the question then that we posed was like, how can we truly detect the presence of quantum correlations in a thermodynamic way? Well, so here, as I said, we assume that we have some arbitrary state prepared in an unknown state, and we allow an arbitrarily thermodynamic process. The only constraint here is that everything is preserving energy because, as I said, we are looking at the shoebox. Energy is just exchanged between parts of the system that I'm looking at. And then suppose that in this experiment, we have access to some thermodynamic quantities, such as the heat exchange in the process. And by heat here, just the energy difference in this process. Just by reading this number, can I say something if this initial state is entangled, or if this initial state has magic, or if it has coherence? And the nice thing is that, yes, we can do. And actually, we can come up with a set of thermodynamic witnesses which allows you to probe quantum correlations. So basically, I could lay down here the way that we do this. But I also don't want to give more information to not make it, let's say, more complicated than what I'm already saying. But here, just let me very quick flash this. So basically, the main assumptions is that we have an arbitrarily multipartite system. We have some thermal environment that we don't fix its size. And then we have a mediator that we just call as quantum memory. And the idea here is that we couple these three subsystems with an energy-preserving unitary and allow them to evolve. So I make no assumptions about the interaction strength, the complexity, the duration, and basically since I don't have an external agent, I'm not injecting or extracting energy. Here, the only energy exchanged between system, memory, and BEF will be accounted for as heat. And I will engineer this memory in such a way that at the very beginning of the transformation and in the end, its state returns precisely in the same state that I prepared. So it just acts as a mediator, just like as a memory. And then you could ask me why I'm doing this. And it basically because a very nice thing that you can prove, which is in the exercise, is that if you couple those systems with an energy-preserving unitaries and you look at the energy difference, which is your heat, only elements in the density operator of your system, which is sitting in the in the degenerated energy subspace will contribute to the heat exchange. But then if you have this mediator, you can access elements which lives in the non-degenerated energy subspace and this gives you a door to access those locked correlations. Okay, there's a mistake there. And then under this, we could ask what is the optimal heat flow in this situation, right? If we would like to probe the energy exchange here. And then basically, just let me flash a bit fast, sorry for this. What we proved is that, well, for this protocol, you can always decompose the energy exchange in this process as a sum of two contributions. For example, if we look at a bipartite system, the first contribution is given by a separable state with the same average energy as your system and the same qubit marginal. So if you have a bipartite state, you look at one marginal, this separable state has the same marginal, plus some quantum contribution. And this quantum contribution is a function proportional to the conditional entropy, which is defined here. And then basically, what you can show is that, well, a fact that it was already known in the literature is that this conditional entropy can be negative, precisely when you have an entangled state, right? Because imagine that if you have a Bell pair, so this would be 0 and this would be log 2, so this quantity is minus log 2. Of course, that not all entangled states will have negative conditional entropy, but if your state has conditional entropy negative, then your state is entangled. So this means that we have a boost in this heat exchange, which comes from entanglement in this case. And another thing that we can prove is that there's a hierarchy in the sense that if I take states which has the same average energy and the same marginals, we can write the following hierarchy. So if I think about heat in my system, so product states will always lay below separable states, which will be always below entangled states. And you could engineer this to come up with heat-based witness. And this is really interesting, right? Because basically those witnesses, they only take into account quantities that you have access, such as like the average energy of your system. So in principle, you could measure this environment before starting your process. You know what is the average energy of this environment, and then you couple with the system, they evolve, you discard the system, and then you measure the environment again, and then you compute this energy difference, and then with the number that you can get, you can see if you violate those witnesses or not. And as a very last example, I consider here an isotropic state, which is just a convex combination between a Bell pair and identity. So it's like a noisy Werner state. And then I apply those results. So basically here what can happen is two scenarios. Either we can cool down the system or we can warm up because we are not restricting anything. So those are the optimal process that you can have. Now, if you ask what is the optimal heat exchange when you have a separable state with the same average energy and the same marginal, what you can get is precisely those dashed lines over there. So this means that everything which is below this dashed line and above the other dashed line are entangled states that you can detect via heat exchange. Of course that this witness is not optimal. And we could also ask what happens if we look at higher dimensional systems, because here I'm restricting to d equal 2, and what is the limit of our detection. And as I said in the previous slide, the limit of our detection is the conditional entropy, right? Because I rely on the fact that this conditional entropy has to be negative, and basically we know precisely what is this lambda critical in which the conditional entropy will be negative. And by solving a simpler equation, we can see that if we start increasing the dimension of our system, our witness gets better and better, but then it saturates at some certain point. Okay, so finally, let me finish. just by saying that this is a very simple example on how you can use this framework to witness the presence of quantum correlations. Here I illustrated with entanglement, but if you would like to detect the presence of coherence, for example, you could do the same. If you would like to detect the presence of magic, for example, you could do the same. And then the nice question is whether we can say something about multipartite quantum correlations. So with this, thank you very much, and really sorry to bombard you with information in this last day. I will be around if you want to talk or discuss or have questions, yes. So, so the question is that if we have a spin chain and then we take parts of this spin chain and treat the other part as some sort of path, if we need this to be in a thermal state. Well, it doesn't need to be in a thermal state per se, but it might be that, well, because here the interesting aspect is that if you have a thermal state, you can freely measure this thermal state, and then you don't care about this thermal state, right? If you have your spin chain, it might be that when you measure this part that you are treating, you collapse the state into something that you don't want, and then you can get a wrong readout. Yes, yes, but you could, for instance, take your spin chain, couple to a qubit, just analyze the interaction between them, and then do precisely the same tools that I'm doing here.